Hello guys, welcome to Self-Help Maths Academy. Today we're going to discuss about one of the important and interesting concept about the algebraic system. Uh, we will discuss today about algebraic system, or it's also called as algebraic structure. So let's see what is this algebraic system is, or what is this algebraic structure is all about. Say, take any non-empty set. What is algebraic system? We'll understand first. Any non-empty set, okay, if I consider it as say G with one or more binary operation. We may take one or more binary operation depending on the algebraic structure what we're talking about. More binary operations. Binary operations. They are satisfying certain laws or postulates. For example, it may be commutative property, or it may be associative property, or it may be distributive property. Okay. If all these properties are satisfying, then we call that non-empty set together with the binary operation is forming the algebraic system. So some of the example for the algebraic system, for example, we have group, which is an algebraic system. We have ring, which is also an algebraic system, and so on. So now in this video, we're going to check about in detail what is the group is all about and what are the postulates it has to satisfy. So let's understand the group. Now, a group is an algebraic system. When I say algebraic system, it's a non-empty set. So if I consider a non-empty set here, G, okay, together with a binary operation dot. So it may be when I think already I discussed the binary operation is denoted by dot or star symbol or this symbol. So all these are the notation for the binary operation. Now we are talking about the non-empty set G together with the binary operation dot. It's said to be group if it satisfies the following properties. So what are the properties then? The first property is closure property. Closure property. What is this closure properties then? The closure property is basically if I take any two elements for all say AB belongs to G, okay, and this implies A dot B belongs to G. It means that whenever you take any two elements in the group, from the set G, you do that binary operation that still belongs to the binary, the group G or the given set G. Then we call it is following the closure property. For example, if you take the natural number set and I consider the operation as say addition operation, then I take any two natural numbers, say 1, 2 belongs to n. When I add 1 plus 2, because my binary operation is addition here, this will be equal to 3. Again, 3 is a natural number which belongs to n. This implies natural number set under the binary operation as addition is having the closure property. So it's closed under the closure property. It's closure property satisfies. Now, the second property we're talking about is the associative property. The associative property. So what do you mean by associative property? When I take again, let me take the same set and I'll be taking the same binary operation. Say natural number set, I'm taking the binary operation as addition. So for before that, this will be for all ABC belongs to G. If I take A dot B dot C, this will be equal to A dot B dot C. If this property is valid, we call that it follows the associative property. So for example, the natural number set under the addition, if I take say 1, 2, 3 belongs to n, under the addition, if I add 1 plus 2 plus 3, this will be 1 plus 5, which is equal to 6. Now on the other hand, if I use this, it is 1 plus 2 plus 3. This is equal to 3 plus 3 again. This is 6. That means the natural number set under the addition binary operation will form the associative property. Now let's see the third property, which is also very important postulate for the given group. That is existence of identity. Existence of an identity. Okay. What is this identity element is all about? And why do we need this? Let's see. So there exists an unique element. We say it as unique because there is no two identity elements exist for a given set. So we have to say that there is a unique element. We talk about unique element. Say we usually denote it by E, such that if you take A dot E or E dot A will be equal to A, this is true for all A belongs to G. So there exists an unique identity element, which is very, very important as I'm talking about the identity element. So for example, if you see Z as an integer set with the binary operation as addition, if I consider, then if you consider an element say -1, if I add this element to 0, I'll get -1. Or 0 you take, add -1 to it, it is -1. So this is valid for each and every element in Z. This implies 0 will be acting as an identity element. So therefore, existence of an identity also is one of the important postulates which has to be satisfied by the group to form the group. Fourth one is existence of inverse. Existence of inverse. What is this? Existence of inverse means for each A belongs to G. If I take for each A belongs to G, there exists an element A inverse belongs to G. A inverse belongs to G such that if you take A with inverse or A inverse with A, you will get an identity element. If this is happening for each and every element A, then we say that A inverse is the inverse element of a given element, given element A. If this is true for each and every element A, then existence of inverse exists for with respect to that particular set. This is around all the four properties. If it is satisfying, then the set G is called the underlying set of group under the binary operation dot, which is called as usually the group operation. Then we call G together with dot as group. G together with dot as a group. So therefore, here we have discussed the four properties, that is closure property. We have discussed associative property, existence of identity, and existence of inverse. So if I just want to note them, let me give the name for these as say P1, postulate number 1, postulate number 2, postulate number 3, and postulate number 4. So if P1, P2, P3, P4 are satisfying, then we call the non-empty set G together with the binary operation as group.
Now, the next important question is every given non-empty set with the binary operation satisfying all these four properties, or is there any non-empty set which is left with only few properties? If that's so, then how do we deal with them, and what is exactly the name for them? Let's see. So there are other algebraic systems which satisfy some of the postulates but not all. So if I take them, for example, say the first one, if only P1 satisfies, only P1 satisfies. P1 means only the closure property is satisfied. Then we call G dot as groupoid. Groupoid. If only P1, that is closure property, satisfies, then we call it as groupoid. Okay. And then if any subset of a, say for example, if S is a subset of G which also satisfies only the P1 property, then we call S with dot as subgroupoid. Subgroupoid. Okay. So this is one thing. Now second thing is if, or it's also called as sometimes the Cauchy group. This we also say it as Cauchy group. Okay. With respect to the composition, that is dot. Then if we have the Cauchy group, means the groupoid, the Cauchy group we have with the identity element, then we call it as loop. We call it as loop. So basically you can remember it as P1 plus P3, where P1 is meant for the closure and P3 meant for the identity element. Then we call it as the Cauchy group, as the loop. And then the third one, if only the postulates P1 and P2 are satisfied, a given set G together with a binary operation, if it satisfies only P1 and P2. When I say P1 and P2 means it has satisfying the closure property and associative property. Then we call it as semigroup. We call it as semigroup. Okay. And then if you have any subset S, which is subset of G, which also satisfies P1 and P2, then we call it as sub-semigroup. Sub-semigroup. Okay. Then let's see. If the G together with the binary operation is satisfying, say, P1, P2, and P3. So it satisfies closure property, associative property, and the identity element are satisfied. Then we call it as monoid. We call it as monoid. And the subset, if I have subset S is a subset of G, which also satisfies these three properties, then we call it as submonoid. We call it as submonoid. Okay. So now the very important, we also take it as the postulate number 5. Okay. So the P5 is commutativity. Commutativity. Okay. So commutativity in the sense we are talking about one more postulate where we are dealing with the group operation. Say, if I say we are talking about the A dot B is equal to B dot A. This is true for all AB belongs to G. If this is happening along with all the four binary operation, if commutativity also holds, then that group G together with dot, we call it as abelian group. It is abelian group, or it's also called as commutative group. It is commutative group. Yes. So this is very important, but not all the groups are forming the commutative group. So few of them may form the commutative group and few may not. So if it is not satisfied, if it is just only P1 to P4 and the commutative group is not, I mean, commutative law is not satisfied, then we call it as non-abelian group. If this is P5 is not satisfying, then we call it as non-abelian group or non-commutative group. Okay. And then let's see next thing what we do. We have finite and infinite group. So if the group is forming on the finite set, then we call it as, if it is the finite set which is forming the group, finite set and which is forming the group, then we call it as finite group. If you're forming the infinite, you're taking the infinite set to form the group, we call it as infinite group. This is infinite group. Infinite set you're considering and you're forming the group, it is called as infinite group. Okay. And now you also see order of a group with respect to the finite set. If I am talking, then the number of elements in the finite group is known as the order of the group. So order of the group, order of the group we are talking about. So it is the number of elements in the finite group. In the finite group is called as the order of the element, order of the group. This usually we denoted by O of G. Okay. So we now we have discussed about the group definition and what are the other properties it satisfies, and if it satisfies only few postulates, what we call them. And now actually it indicates that not all the sets are satisfying all the properties under the given binary operation. So we may be coming up with the examples with respect to the group in the next video. Okay, so this is all in this video, guys. In the next video we'll come up with the examples on the group and the other stuff. So till then, take care.